All right, so the product rule. Now, a lot of times when you write these rules, and depending on the notation you can get really complicated looking rules. And so what I want to do is I want to skinny this thing down so you really see what the rule is telling you, rather than being clouded by a lot of things. And so here I'm writing f and g as functions, okay? So rather than writing f at x times g at x and then take the derivative of that and having all those x's in parentheses, I'm just writing this down as a function without the variable showing. So what this rule is all about is that if we want to take the derivative of something that has a product in it, we can't just take the derivative of each of the factors and then multiply it together. I think I showed you that on Monday. So what you need to do is we need to take the derivative of the first function and multiply it by the second function, and then multiply it, or then add it to the first function times the derivative of the second function. Now, depending on what textbook you've used before, if you've taken calculus in high school, or some books that you'll find around here, like if you're reading Stewart's calculus book, which was the former textbook for this class, you might see that the order of these things change. Okay, so notice f and g are in the same order, and then we take the derivative of the first one and we take the derivative of the second one in that order. For this, it doesn't really matter. A lot of textbooks will say f times g at prime, or g prime, plus f prime times g. That's the same thing, right? If you commute it. But when we get into the quotient rule, where this is a difference, it's going to be very important to get the sign right. So please abandon anything you've known before about the product rule and follow this format, because it'll just make it that much easier and more consistent. Okay, so let's go over a couple things, couple examples here. All right, now here's a product that any sensible person would just say, oh yeah, that's x to the fifth, and then take that as a derivative of x to the fifth. That's just 5x to the fourth, right? But I'm going to show you the product rule just to see how this works. I'm going to treat the first function as this x cubed, and the second function as this x squared. Notice I'm not trying to write it out, defining with function names. So I take the derivative of x cubed and I get 3x squared. And then I take my second function and just write it without doing anything to it. And then I'm going to add that to the first function, which is x cubed, and then multiply it by the derivative of the second function. So I got this thing going. And so one caution, when you're applying derivative rules, just apply the rule. Don't start simplifying along the way. Write everything down, and then once you've taken the derivative, then simplify. Okay, so you're not going to be able to keep track of everything with more complicated expressions if you try and simplify along the way. So here this is very simple. And use parentheses if you want, by all means. The derivative times the function, and then the function times the derivative. So now if I then multiply this, I get 3x squared times x squared is 3x to the fourth. X cubed times 2x is 2x to the fourth. And I add these two, and I get 5x to the fourth. Now that's exactly what I get when I've multiplied those together and I get this. So no matter what route you take in differentiation, you should get the same answer. It may not always be easy to simplify it to the point where you get the same answer, where the answer looks the same, but it will be the same answer. So, of course, the product rule would never be used on this, right? You would just multiply it out and use the power rule. But this is just to show you the basic format of the product rule and how you're to do this. Okay, any questions so far? Okay, so with polynomials, you can do either thing. You can either multiply them out, like let's say we have two longer polynomials, x cubed plus 2x plus 1 times x squared plus 1 or minus 1 or whatever. You can do it either way. You can either multiply it out and take the derivative, or you can use the product rule, take the derivatives of each part, and then add them all together. With other functions, and this will really apply to math 14 when you're dealing with things like e to the x and the sine of x and all these other functions that don't really have a simple, really can't simplify if you multiply x times the sine of x. There's no simplification. You'd have to use the product rule. These are essential. Okay, so where that leaves us is that we're dealing primarily with rational functions now and algebraic functions, functions involving roots and powers and things like that. So that's how we're going to apply the product rule. And usually there's more than one way to do it. Okay, so those first few examples, I think one way will be much more obvious than the other. Okay, so let's look at radicals now. Let's say we have this. Okay, we have two ways of doing this. We can either use the product rule directly, or we can multiply the x squared times the square root of x, distribute, and then 1 times the square root of x. So let me first do it with the product rule. Okay, so I'm going to treat this x plus 1 as my first function, and square root of x as my second function. So I'm going to take the derivative of the first function, which is just 2x, times the second function. Then I'm going to take the first function times the derivative of the second function. Okay? And so then I'm going to simplify. I'm going to distribute this 1/2 x to the minus 1/2, and so when I multiply that times x squared, I get 1/2 x to the 3/2, and then I'm going to multiply this here and get 1/2 x to the minus 1/2, and then probably write it so it all has radicals, and this will be an adequate answer. Well, I guess I didn't simplify it completely. I had an x square root of x in both of these, so then I can add those two together and get 5/2, and then I rationalize the second one to get this. Now, combining these two, I would say it's important. Rationalizing this, for me, it's not important. Okay, so you could have left this as 5/2 or 5x square root of x over 2 plus 1 over 2 times the square root of x. So any variation of probably these two things, with the exception of you must combine this, is a perfectly good answer. Okay, any questions on the process there? Okay, so let's do it the other way. And you might find this is easier. So I'm going to take my function and I'm going to distribute the square root. So I get x squared times the square root of x, and then just the square root of x. And so I'm going to put those into exponential forms, and then I'm going to take the derivative and then rewrite it. And I get exactly the same thing. And like I said, either of these two are fine. You don't need to rationalize it unless I ask you specifically, rationalize the denominator. Now, this is probably the easier way to do this particular problem, but I'm showing you this just to get you used to what the product rule looks like, because you won't always be able to do it this way, the alternate way, this way here. Okay, so there's nothing like trying it yourself. Okay, so it's possible to multiply these out and just use the power rule, and I would probably advise you to normally do that if you just have simple polynomials like this. But here, since we're learning the product rule, please do it by the product rule. And then this one, I think, is much easier to do with the product rule. All right, so let's look at this. We have the first function is logically x squared plus x. Second function is 2x plus 1. So the derivative now is going to be the derivative of this one, which is 2x plus 1, and then we have a 2x plus 1 for the second function. And then we take the first function, unchanged, and we take the derivative of the second function, which is 2.
Wouldn't it be 3? Doesn't the x become a 1? Yeah. And then 2 plus 1 is 3. No, the derivative of 2x plus 1.
Where's should be a 3?
Like, avoid the single 2.
No, it's just,
Because doesn't x become a 1?
yeah, it's 2x to the first, so 1 times 2 is 2, excuse me. So the derivative of 2x plus 1, think of it, it's the line, slope is 2.
Oh, and the 1 goes away.
The 1 drops to 0.
Oh, okay, I added it.
Right, the derivative of 1 is 0. Okay, so then it's a matter of expanding this and then adding it all together, and so that's what you get. Any questions on this one? Okay, so I'll have this all written out. So we're going to take first the derivative of the first function. So this is, of course, x to the 1/2. So now we'll take the derivative of that, which is 1/2 x to the minus 1/2. The derivative of 1 is 0, so we don't write anything there. And then we write the second function. Then we're going to add that to the first function, square root of x plus 1. And then we're going to take the derivative of this. Remember, this is x to the minus 1. So we're going to have negative x to the minus 2. And then the derivative of negative x is negative 1. All right, so now this is the derivative. Now the task is to simplify that. Okay, everybody follow how we got that? Okay, so the first thing to do is expand the two binomial expressions we have, or I guess this is a monomial times a binomial. So then here this becomes 1/2 x to the minus 1/2 times x to the minus 1. We're going to have 1/2 x to the minus 3/2. And then we're going to have x to the 1/2, or 1/2 x to the minus 1/2 times negative x is going to give us negative 1/2 x to the 1/2, right? Minus 1/2 plus 1 is 1/2. And then we'll take, this is x to the 1/2 times negative x to the minus 2, and we get negative x to the negative 3/2. Square root of x times negative 1 gives us negative x to the 1/2, and then 1 times negative 1 is negative 1. So there's all of our terms, and now we examine this to see, okay, we have one pair here with the negative 3/2 exponent, and then we have a pair here with the exponent of 1/2. And so we'll rewrite all that, combining our, so we have 1/2 minus 1 is negative 1/2, and we have negative 1/2 minus 1 is negative 3/2, and then we have negative x to the minus 2 minus 1. And I think I have one more line of writing this like that. Any questions?
Are we likely to have something that complicated on the test?
This is still simple,
That's still simple.
That's hard.
Uh-oh.
okay?
That was simple.
All right, so let's take a look at the quotient rule. The quotient rule, let's say we have two functions and we want to take the derivative of it. We're going to take the derivative of the first one times the second one and then minus, and this negative sign is crucially important, the first one times the derivative of the second one. It's going to all be over the denominator function squared. Okay, so I'll do an example. All right, not too bad of a function, x squared plus x over x plus 1. And I've written the numerator function in green, the denominator function in red, so you can perhaps follow along more easily. So what I'm going to do here is I take the derivative of the first function, the numerator function, 2x plus 1, multiply it by the denominator. Then I'm going to subtract the numerator function times the derivative of the denominator function. And here, that's just 1, right? X plus 1, the derivative of that is just 1. And then I'm going to put that over x plus 1 squared. Now, a piece of early advice here, don't expand the denominator yet. Okay, you may end up expanding it, you may not need to. It's likely you probably won't need to. Okay, so now we need to simplify the numerator. And so we're going to take 2x plus 1 times x plus 1, and we get 2x squared plus 3x plus 1. And then we're going to distribute this negative. Treating this negative sign properly is probably one of the biggest sources of errors. I mean, you can understand this perfectly, but make sure you're applying the negative properly, through distribution. Because that's one of those kind of mistakes that you make, you slap your forehead, because I know you understand it. It's just a matter of always doing it reliably. And so then we have this still over x squared plus 1. So I'm going to simplify that numerator. And so I get x squared plus 2x plus 1. And guess what? That factors. And we got 1. The derivative is 1. Why do you suppose the derivative is 1 on this one? Any questions? All right, let me show you a different one. 1 over x plus 1. Now this is something that we'll take the quotient rule. But notice the function in the numerator is just 1. All right, so this is actually not too bad, because we'll take the derivative of the numerator. So that could be a 2 or a 5 or any constant, and the derivative is 0, right? And then it's going to be minus 1 and then times 1, which is the derivative of x plus 1. Okay, everybody understand the numerator? And then the denominator is just the denominator squared. So when I simplify it out, I get negative 1 over x plus 1 squared. That's not too different than if you would, than if you just took the derivative of 1 over x, right? Remember what the derivative of 1 over x is? That's just negative 1 over x squared. It's not too different. Okay. Another example, x squared over x plus 2 squared. Okay. Derivative of the, in this case, we can either expand this or we can treat it like this. The problem is that you don't know what the derivative of x plus 2 squared is yet, right? You don't have any tools for that. So what I'm going to do is I'm going to expand this, because I can take the derivative of this. I can't right now. Friday you'll be able to take the derivative of x plus 2 squared. But now we have to expand it to make the polynomial. Okay, so the derivative then is we take the derivative of the numerator times the denominator. And then we're going to subtract the numerator times the derivative of the denominator. Okay? F, or f prime g, f g prime. Okay? And then, now, I needed this expanded because I needed to take the derivative of it. But I didn't change its value. And taking this squared will make a mess. I can just take this one squared and say it's x plus 2 to the 4th. So I'm saving myself a little factoring ultimately, that if I have things to cancel, I want factors. I don't want an expanded polynomial. So that's why I'm retaining this and then saying it's to the 4th. I just expanded it here so I can get the derivative up in the numerator.
Why are you saying it's to the 4th?
Because I have to square the denominator.
Okay.
Okay, so I'm going to expand that, that numerator to see what it simplifies to. And when it's all said and done, I get 4x squared plus 8x with all this mess. And then I can notice, oh, I can factor out a 4x here, and I get x plus 2. And that I have as my factors in the denominator, so I can cancel one of them out, and I get 4x over x plus 2 cubed. Now, one of the things that I like to do sometimes is avoid using the quotient rule by using the product rule. And the way that you can do that is you can change the denominator, oftentimes, into a product with the numerator. Like this would be 1 times x plus 1 to the minus 1, or here this would be to the minus 4, or minus 2 in the numerator. It doesn't work with this so much directly, but you'll see in other functions, by taking a product of two things, one of which has a negative exponent, sometimes is easier than using the quotient rule. We'll have plenty of examples of that on Friday when we use the chain rule. Okay, but for now, it's time for you to try the quotient rule. Where's the fan?
Can we open the door? It's like
Yeah.
significantly cooler outside. I'm just saying maybe open.
Now what we need to do is put the fan in a place where it's blowing stuff out to draw in cool. So can we move the fan over to the corner? No plug? Okay, then maybe we can move the fan right up here and actually draw it in.
Come on, engineers.
So we have to expand this one?
Don't expand it.
The top?
Oh yeah, you will have to expand it, that's right. You don't know how to take the derivative of this directly, so you have to expand it so you can take the derivative of it.
Oh.
Here, which one do you- And then we have the back windows open. Is the sun falling on the shade? It is, isn't it?
Yeah.
Okay, hopefully this will draw in some air. Is that okay on your eyes? It drives my wife nuts where it dries her eyes out. When she gets it blown in her face. Okay.
Just with the door open,
That's anywhere.
so they, like, I think they get dry.
Yeah. Okay. Good. Gosh, you can already feel the difference, huh?
Just with the door open, like, we felt like a breeze.
Did you?
Yeah.
I just like to make you sweat, that's all.
How kind.
Okay, that's sweet, right? Okay. So, how does that numerator expand? It's just x squared plus 2x plus 1, right? All right? So expand it. Now I was saying there's two ways here. When I was talking about using the denominator in the numerator, or the reciprocal of the denominator, and applying the product rule might work a little easier here. But anyway, so we have this. So how about then, ooh, we only have 2 more minutes. I thought we had 45 more minutes. I'm sorry. Okay, so we take the derivative. Just kidding. Take the derivative of the numerator times the denominator. Take the numerator times the derivative of the denominator. Take the difference, and then we square the denominator. Okay, and then we're going to expand it. Collect all the terms, factor out an x. You did it. Excellent, right? This is one way to do it. The other way to do it now is to write it like this. where I'm going to divide through this x squared first. Okay, so I could take x squared divided by x squared is 1. 2x divided by x squared is 2 over x. 1 over x squared is just 1 over x squared. This is a much easier derivative to take now, right? Okay, so I'll post this so you can study it, but